Hello. In our previous lesson, we covered what an LDR is and how it operates. In this lesson, we will reinforce the topic by creating an application where an LED lights up in the dark. Let's begin by analyzing the circuit phase via the Tinkercad application. Then we'll analyze how the circuit operates in a physical setting. First, we add the Arduino board to our workspace. Next, we choose the breadboard. Using a small breadboard would be suitable. After that, we will add the circuit components. We'll add an LED and set its color to green. We'll proceed by adding a resistor to accompany the LED. The resistor's value is 330 ohms, identified by orange-brown bands. After that, we add the photoresistor or light-dependent resistor. After placing the photoresistor in the workspace, the next step is to add a resistor that will work with the LDR. The value of this resistor will be 10 kiloohms, indicated by brown, black, and orange bands. All our circuit components have now been added. We'll relocate the circuit components to the top to avoid any obstruction while creating the circuit diagram. To start, we provide 5 volts power to the breadboard. We can change the wire color to red for the power supply. We follow by transferring the ground line to the breadboard and color this wire black. Now we can place the components on the breadboard. We start by placing the LED on the breadboard. We connect the short leg of the LED to the ground rail and make the wire black. To prevent damage to the LED, we need to connect a resistor to its long leg. We rotate the resistor sideways and place it. Next, we will control the LED from digital input-output pin 3, so we connect the resistor attached to the LED's positive leg to pin 3. After that, we place the photoresistor on the breadboard. We apply a 5-volt supply to any leg of the light-dependent resistor and set the cable color to red. Then, we will place the 10 kilo-ohm resistor onto the breadboard. Before that, we rotate it sideways and connect it to the right leg of the LDR. We connect the other leg of the resistor to the ground rail, and we'll set the wire color to black. Subsequently, we'll proceed to read the LDR information using analog methods. Analog input A0 is connected via a wire to the junction of the resistor and the leg of the LDR selected as the ground. We can change the color of this cable to orange. The circuit diagram is now complete. Let's move on to the coding part. You can set up the circuit diagram in a physical environment as demonstrated through the Tinkercad application. And you can write the codes in the Arduino IDE and upload them to the Arduino board. Both the circuit diagram and the code writing are now ready to be displayed in the same window. Let's start working on the code. We define an integer variable named pin and set its value to 3, since the LED is attached to digital pin 3. In the setup block, we first initialize serial communication. To do this, we code serial.begin 9600 for setting the serial communication rate to 9600. Following this, we will configure the pins with the pinMode command. PinMode pin output sets pin 3, to which the LED is connected, as an output. In the loop block, we first define a variable of integer type. We name the variable LDR value and set its value to the analog reading from a 0. We use the analog read function for this and indicate the pin to read the analog value from in the parentheses. Subsequently, we print the variable's value to the serial monitor using serial.println for monitoring. Then, if the variable's value is 250 or less, the code within the curly braces will be run. Inside the curly braces, the pin represented by the variable is set to high, allowing current to flow through pin 3. In brief, if the variable LDR value is less than or equal to 250, meaning the environment is dark, the digital write command ensures that energy is drawn from pin 3, which was set as output in the setup section. Thus, the LED will light up. If the variable's value is not less than or equal to 250, it means the environment is bright, and the digital write command sets the pin associated with the pin variable to low, cutting off the energy and turning off the LED. We then use the delay command to create a 500 millisecond delay, meaning the ambient light level will be evaluated every 500 milliseconds. Let's start the simulation. Once the simulation starts, we can adjust the light falling on the LDR by clicking on it. Right now, we observe a value of 54 on the serial monitor and the green LED is on. When we slide the scroll bar to the right, increasing the light level reaching the LDR, the LED turns off once it exceeds 250. When we move the scroll bar to the end, 974 appears on the serial monitor. Arduino uses an analog to digital converter to convert the analog voltage of the photoresistor into a digital value. The ADC on Arduino Uno has a 10-bit resolution, meaning it can represent the input voltage as a value between 0 and 1023. An input voltage of 0 volt corresponds to a digital value of 0, and an input voltage of 5 volts corresponds to a digital value of 1023. Intermediate voltages are linearly mapped within this range. In other words, we provided a 5-volt voltage to the LDR. This voltage will produce varying values at the output pin, which will be between 0 and 5 volts. We can observe these values digitally as 0 to 1023 via the ADC. When we reduce the ambient light again and it drops below 250, the LED will light up once more. Now, let's start examining how this application will work in a physical environment using the Arduino IDE. After writing the codes through the Arduino IDE software, we check the port from the Tools section and upload the codes. Once the codes have been uploaded to the Arduino board, we can analyze the operation of the circuit. You can see the circuit working on the screen when the lamp is on or off. We can achieve the same result when we block the light reaching the LDR ourselves. We have reached the end of the example related to the light-dependent resistor. Have a good day.